For millennia, humanity viewed the universe as a vast, unchanging stage. We perceived three dimensions: length, width, and height. These dimensions defined our reality. Time, on the other hand, flowed eternally and uniformly. It was an independent entity, unaffected by the events unfolding within the cosmos. This Newtonian worldview provided a comforting sense of order. It shaped our intuition and guided our understanding of the natural world. The laws of physics, as formulated by Isaac Newton, reigned supreme. Objects moved across the cosmos like actors on a stage. Their movements were predictable, governed by the forces of gravity. The universe in this classical picture was a giant clockwork mechanism. Each part moved in perfect synchrony, ticking away with unwavering precision. However, beneath the surface of this seemingly ordered cosmos lay a profound mystery. Newton's theory of gravity, while remarkably accurate, could not explain the force's true nature. What was the mechanism by which objects attracted each other across vast distances? This question, among others, hinted at the limitations of our classical understanding. A revolution in thought was brewing, one that would forever alter our perception of the cosmos. In the early 20th century, a young Albert Einstein shattered the foundations of Newtonian physics. His theories of special and general relativity revolutionized our understanding of space and time. He imagined a universe where space and time were intertwined entities. Einstein's first breakthrough came with the theory of special relativity. Published in 1905, it explored the constant speed of light for all observers. This meant our measurements of space and time were not absolute. Time itself must dilate for the observer in motion. Einstein's general relativity, published in 1915, extended these ideas to include gravity. He realized that gravity was not a force acting at a distance, as Newton had proposed. Instead, it was a manifestation of the curvature of spacetime itself. Massive objects like stars and planets warped the fabric of spacetime around them, much like a bowling ball placed on a trampoline curves the fabric. This curvature of spacetime dictated the paths of objects moving within its influence. Planets, for instance, did not orbit the sun because of a mysterious force pulling them inward. Rather, they followed the curvature of spacetime created by the sun's mass, much like a marble rolling around the depression created by a bowling ball on a trampoline. Gravity, in Einstein's view, was not a force but a consequence of the geometry of spacetime. This revolutionary insight had profound implications for our understanding of the universe. It explained the anomalous precession of Mercury's orbit, which had puzzled astronomers for centuries. It also predicted the bending of starlight around massive objects, a phenomenon later confirmed by observations during a solar eclipse in 1919. Einstein's general relativity had passed its first major tests with flying colors, forever changing the landscape of physics. Special relativity, a dance of time and motion. To grasp the mind-bending concepts of special relativity, let's revisit the analogy of the train and the platform. Imagine a beam of light bouncing vertically between two mirrors inside a stationary train car. An observer on the platform would see the light travel a longer, diagonal path compared to an observer inside the moving train, for whom the light simply bounces up and down. Since the speed of light is constant, and distance equals speed multiplied by time, the observer on the platform must conclude that time is passing slower inside the moving train. This phenomenon is known as time dilation. The faster an object moves, the slower time passes for it relative to a stationary observer. Special relativity also predicts length contraction. The length of an object moving at high speed appears shorter in the direction of motion from the perspective of a stationary observer. These effects might seem bizarre, but they have been experimentally confirmed countless times. They highlight the interconnectedness of space and time and the relative nature of our perception. Beyond Einstein, peering into the quantum realm. Einstein's theories revolutionized our understanding of gravity and the large-scale structure of the universe. However, they also revealed a profound mystery: the incompatibility of general relativity with the world of quantum mechanics, the theory governing the behavior of matter and energy at the atomic and subatomic levels. Quantum mechanics, developed in the first half of the 20th century, introduced a probabilistic view of the universe. Subatomic particles like electrons and photons were no longer seen as tiny billiard balls but rather as waves of probability, their positions and momenta inherently uncertain. This inherent fuzziness contradicted the deterministic nature of general relativity, where the curvature of spacetime dictated the precise trajectories of objects. The quest to reconcile these two pillars of modern physics has been one of the greatest challenges in theoretical physics. One promising approach is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings, vibrating at different frequencies, give rise to all the fundamental forces and particles in the universe. The Large Hadron Collider unveiling the secrets of the universe. To probe the fundamental nature of reality and test these groundbreaking theories, scientists have built the Large Hadron Collider, the world's largest and most powerful particle accelerator. Located at CERN, the European Organization for Nuclear Research, the LHC accelerates beams of protons to near the speed of light and smashes them together in colossal detectors. These collisions recreate the conditions that existed fractions of a second after the Big Bang. By analyzing the debris from these collisions, physicists hope to uncover the secrets of the early universe and the fundamental constituents of matter. The LHC has already yielded groundbreaking discoveries, including the detection of the Higgs boson in 2012, a particle responsible for giving mass to other particles. The LHC continues to push the boundaries of our understanding, searching for evidence of supersymmetry, extra dimensions, and other exotic phenomena predicted by string theory and other theories beyond the standard model of particle physics. Each new discovery brings us closer to unraveling the deepest mysteries of the cosmos. The ethical frontier of dimensional exploration. As we delve deeper into the fabric of reality, we encounter profound ethical considerations. The possibility of creating microscopic black holes at the LHC, for instance, raise concerns about potential risks. While these concerns have been largely addressed by scientific studies, they highlight the importance of responsible innovation and open dialogue between scientists and the public. The tantalizing possibility of discovering extra dimensions also raises profound philosophical and ethical questions. If other dimensions exist, what are their properties? Could they harbor other universes, perhaps with different laws of physics or even different forms of life? And if we could access these dimensions, what would be the implications for humanity? These questions lie at the forefront of scientific exploration and philosophical inquiry. As we continue our journey to unravel the mysteries of the universe, we must proceed with both curiosity and caution, driven by a thirst for knowledge and a deep respect for the profound implications of our discoveries. The journey to understand the mind-bending reality of spacetime is far from over, and the discoveries yet to come promise to reshape our understanding of the universe and our place within it.